Hello students, the title of this experiment is Voltage Series Feedback Amplifier. Here is the disclaimer. So this is the outline that we are going to follow. So here is the block representation of Voltage Series Feedback Amplifier. So you can make out there are two things involved here. One is the sampling point. Okay, here this is the sampling, and here this is a mixing point or simply a comparator. Now in case of a voltage series, a part of the output signal, so here when I say a part of the output signal, it is a voltage which is sampled and which is connected back with a feedback fraction. Amount of the feedback is controlled by this value of beta. Now here you see it is connected in series, so this topology is referred to as voltage series feedback. So when any increase in the output signal results into the input in such a way as to cause the decrease in the output signal, the amplifier is said to have a negative feedback. Now the advantages of providing negative feedback are that the transfer gain of the amplifier with feedback can be stabilized against the variations in the hybrid parameters of the transistor or the parameters of the other active devices used in the circuit. Now the most advantage of the negative feedback is that by proper use of this, there is a significant improvement in the frequency response and in the linearity of the operation of the amplifier. Although this offers certain disadvantages, it includes the voltage gain. You see here, by employing a negative feedback, the voltage gain is decreased. Now in case of voltage series feedback, the input impedance of the amplifier is increased and the output impedance is decreased. Also the noise and the distortions are reduced considerably, and the common collector or this emitter follower is as shown in the figure. It's an example of voltage series feedback since the voltage developed in the output is in series with the input voltage as far as the base emitter junction is concerned. So you can make out here the output is taken from the emitter as far as the emitter follower is concerned. So the signal is going to drop across this resistor, the output voltage, which also acts as a feedback voltage with respect to base emitter junction. Now this is a single stage RC coupled amplifier without emitter bypass collector across RE. R1 and R2 provides the base bias. The emitter follower inherently exhibits 100% negative feedback since the voltage at the emitter follows the input voltage. And using the demonstration videos, we can actually make out this. Now you see here in this circuit, the output voltage is taken across RE, or if I look from this end, this acts as a load resistance, so I can say RE equals to RL, and the feedback ratio beta equals to RE by RL. Now here they cancel out each other, so beta equals to 1. So if I talk about the overall voltage gain with feedback, the equation is AF equals to A upon 1 plus A beta. So beta equals to 1. So the equation reduces to A upon 1 plus A. So which is little less than the unity. And then there are certain characteristics of an emitter follower. As far as current gain is concerned, AI equals to 1 plus HFE. We will not derive this again in the practical session because we have already derived this in the classes. So you can again refer to those lectures available online. And then input resistance here equals to HIE plus 1 plus HFE into RL. Voltage gain is AI RL upon RI, which equals to 1 minus HIE by Ri, and R naught equals to HI plus RS divided by 1 plus HFE, and R naught F, that is the feedback, the output resistance with feedback, equals to R naught in parallel with RL. These are the different combinations, like we have voltage series feedback, voltage shunt feedback, current series feedback, and current shunt feedback. Now this series of feedback connections tends to increase the input resistance, while the shunt feedback connections tends to decrease the input resistance. Also, the voltage feedback tends to decrease the output resistance, while the current feedback tends to increase the output resistance. So you can make out from this table. It is desirable that most cascade amplifiers need to have higher input resistance and lower output resistance. Now this voltage series type of feedback has the high input resistance, low output resistance. Now why do we have low input resistance to begin with for this transistor? Now you see, the signal is applied to the base, and base emitter junction is forward biased, so the input resistance offered by a transistor is low. Now it is desired to increase the input resistance, so we connect it in a voltage series fashion. So the moment we connect the circuit in voltage series feedback amplifier topology, the input impedance increases heavily, and that is what is desired if we have to work with the very signals of a very low magnitude of weak signals. On the other hand, the current shunt feedback has the least desirable effect, since it decreases the input resistance and increases the output resistance. So overall, this is a comparative study. I hope this is clear to all. Now the aim of this experiment is to verify the input output waveforms of voltage series feedback amplifier and to observe the voltage gain of the same. Here again are the components required. So you see, this circuit is similar to what we have studied in the first experiment. The only difference, if you observe, is that in the first experiment, that is current series feedback amplifier, the output was taken from the collector terminal. Here the signal output is taken from the emitter terminal. So this circuit is a common collector circuit, and it is referred to as emitter follower because the output follows the input. So we are going to get the same signal at the output. Then again, that's the very same fundamental question, why are we using this? The simple reason is, this particular circuit, that is emitter follower, has got very high input impedance and very low output impedance that is desired. So here is the circuit diagram. These are the component values. When we work with any amplifier circuit, first you make sure that your transistor is working. You have to check out its base terminals voltages and its HFE value. Next, you have to mount the circuit properly with component values of R3, R2, R4 and R1. So this is your biasing network, and you have to note down what is the output voltage and the output current IC. So once this circuit is working perfectly, okay, then only you apply the test signal of 1 kilohertz and now input voltage of 10 millivolts or 20 millivolts. Now when you check the voltage across VCE, it should be typically half of your VCC. If the VCC is 12 volt, we should primarily get here output voltage as 6 volt, and that will ensure that the Q point is right at the center of the DC load line. Once this is working, you have to apply a signal of 1 kilohertz and 20 millivolts. This is a test signal, and if all the connections are properly done, you will get the output to be observed on the CRO. Now you see here a capacitor has been connected. This is the bypass capacitor which is connected across this emitter resistance. Now if I close this switch, then the feedback ceases to exist, and if I open the switch, then there exists a feedback. Fine. These capacitors are used to block the DC components and to pass only the pure AC signal. So what all we required here to perform this experiment? These are the components. Then we do require CRO. Then this signal is derived from function generator. you require a power supply which can give us a voltage of 12 volts. Fine, this is all about the circuit diagram. Here is the theory. You can pause this screen and you can go through it. Then as far as the bandwidth is concerned, it is plotted from 3 dB down from the maximum gain. So if this is the frequency response, it will vary from 100 Hz to 1 megahertz, and this is the plot what you are going to get. This is referred to as mid-band gain. Now typically what we expect theoretically is that you should get something like this, meaning all the frequency components, meaning signal of all the frequencies should be equally amplified. This is a plot of gain 20 log of V0 by Vi. So Vi is kept constant, and if I vary the frequency from 100 Hz to say 1 megahertz, I should get almost the same output for a given fixed input. But that is not the case. You see here, initially when the frequencies, if I take condition here, if the frequency is 0, then when the frequency is 0, that means it's a DC voltage. So this DC signal will be passing through this wire. So the very first element or the component that will present here is the capacitor. So capacitor has got the resistance which is referred to as reactance given as Xc equals to 1 upon 2 pi Fc. Frequency, since I said it's a DC voltage, frequency is 0, so the reactance, that is the resistance offered by the capacitor, will be infinite. So there is no chance of signal crossing the other side of the capacitor. Fine. So if no signal is reaching at the base, so naturally you won't have any output. So you will have a 0 output for a DC voltage, irrespective of your magnitude. The magnitude can be 10 millivolts, but your frequency, if it is 0, then there won't be any signal reaching at the base terminal of the transistor. So there won't be any current activity here. Now as I keep on increasing the frequency, right from say 100 Hz to 1 megahertz, and you have to use steps 1 to 5, 7, meaning on the function generator, set first the frequency to 100 Hz, input voltage to 20 millivolts, note down the output voltage, then make it to 200 Hz, 500 Hz, 700 Hz, then 1K, 2K, 5K, 7K, 10K, and so on. Fine. So as to cover the entire profile of the frequency response. Now as the frequency increases, the reactance offered by the capacitor will reduce, and at certain point your entire signal will be available at the base, that is towards the mid band. And at very high frequencies, the frequency roll off do take place, and again there are junction capacitances. The output resistance with feedback decreases by a factor of 1 plus AV beta, and the input resistance with feedback increases by a factor Ri into 1 plus AV beta. So each topology is going to offer me a separate set of input and output resistances. So you can pause this slide and you can go through it. The most important is when we mount the circuit, we have to see to it that the connections are made proper. So there has to be a continuity between the circuit components. Fine. So you can go through it. The important point is the fifth one. Keep the input voltage constant at 20 millivolts peak to peak. This is using a function generator. This is the observations table. These are the model waveforms. The blue what you see is the input signal, red is the output voltage. These are the precautions to be taken. So while taking the observations for the frequency response, the input voltage must be maintained at constant value of 20 millivolts. Now, so here are the results. After watching the demonstration video, you have to write the conclusion yourself. So what you have observed, and you can download the experimental write-up from this provided link. And now we will move on to the demonstration.
Hi friends, okay, now this was the first experiment that we had done. It was current series feedback amplifier, okay, and then we had tried to find out what is the voltage over here. okay, and then we checked the output of this amplifier with feedback and without feedback. Okay, so when the capacitor was there, it was like there was no feedback. Okay, and then when we had to remove this capacitor from the circuit, there was a feedback, and that was the reason the output was decreasing heavily. That we have seen properly in the experiment number 1. Okay, now today we'll be learning about voltage series feedback amplifier. It is the circuit for voltage series feedback amplifier is same as what is for current series feedback amplifier. The only difference is your output is taken across the emitter over here. Okay, in the previous case the output was taken across the capacitor, across the collector. Now here we are taking output across the emitter. Now if you as I already discussed in the theory, okay, now this particular circuit is used as an emitter follower. Okay, it is very famous circuit that is used. Okay, now what is the emitter follower? The output follows the input. So if you actually connect this circuit, okay, if you give an input over here, if you take an output over here, you will find that input is equal to output. Okay, so then what is the use of this circuit? Now this particular circuit has very high input impedance and very low output impedance. So that is the reason we use emitter followers in many of the circuits. Okay, so the circuit actually is the same that we have done for our first experiment. Only the output is only the place where we are taking the output changes. Okay, at the emitter. So we come here. So this is the same circuit that we have done in the first experiment. Okay, now what we have to do is that, okay, I'll just explain. This is emitter, this is base, and this collector. This is the same first circuit. It is same dot. Okay, so what we'll do is that we'll just turn it on and we'll see. Okay, so we'll turn on the power supply. Just turn on the power supply. Okay, so we have set it to 12 volts. Okay, I'll give some input. Yes, I have given some input via function generator. Okay, I'm not changing it, and I'm turning on the CRO. Okay, what I've done is that I've used 2 channels. Okay, one to see the input, one to check the output. I have connected the channel 2 to the emitter, and channel 1 I have connected to the input over here. So these 2 points I'm checking. Okay, this is one point, this point, and this point. Okay, now we'll see what comes. Okay. Okay, so see, I have put it in dual mode. Okay, so in emitter follower, what will happen is that inputs will follow the output. Okay, so if you see these 2 waveforms, they are exactly same. Okay, so one is output waveform, this is output waveform, and this is input waveform. Now if you see them, okay, they are actually exactly same. Okay, so this is what you need to learn in this voltage series feedback amplifier concept, that it works as an emitter follower, where the gain is 1 and your input is exactly replica of, or your output is exactly replica of the input. Okay, so this is why we require this. Okay, thank you very much.